The Arithmetic Logic Unit, ALU, is like the calculator inside a CPU. It takes two numbers or a number and a control bit from the registers, performs a single operation such as addition, subtraction, and, or shift, and sends the result back to a register or to the next stage of the pipeline. In a typical von Neumann CPU, the data path looks like register file to ALU to register file or memory. The control unit tells the ALU what to do by supplying an opcode, while the surrounding circuitry such as buses, multiplexers, and flag registers moves data in and out. Without an ALU, the processor could only move data. It could not compute, compare, or decide how to branch, so the ALU is the heart of the thinking part of the computer. Operations that an ALU can perform are usually grouped into four categories: arithmetic, addition, subtraction, increment, decrement, and sometimes multiplication or division. Example, a plus b. Logical bitwise and or XOR not. Example, a and b. Shift, logical left shift, logical right shift, arithmetic right shift, rotate. Example, a shifted left by 1. Comparison, set on less than, equality check, greater than. These usually produce a single bit flag, for example Z for 0, N for negative. Truth table for the AND operation. When A is 0 and B is 0, the result is 0. When A is 0 and B is 1, the result is 0. When A is 1 and B is 0, the result is 0. When A is 1 and B is 1, the result is 1. 1-bit addition with carry-in. Row 1 carry-in 0 is 0, B0 gives sum 0 and carry out 0. Row 2 carry-in 0 is 0, B1 gives sum 1 and carry out 0. Row 3 carry-in 0 a 1, B0 gives sum 1 and carry out 0. Row 4 carry-in 0 a 1, B1 gives sum 0 and carry out 1. Row 5 carry-in 1 a 0, B0 gives sum 1 and carry out 0. Row 6 carry-in 1 a 0, B1 gives sum 0 and carry out 1. Row 7 carry-in 1 a 1, B0 gives sum 0 and carry out 1. Row 8 carry-in 1 a 1, B1 gives sum 1 and carry out 1. A bit parallel ALU processes all bits of an operand at the same time. Imagine a line of workers, each handling one digit of a number simultaneously. The whole addition finishes in one clock cycle, ignoring internal gate delays. This is the most common style in modern CPUs because it gives high speed, but it consumes more hardware, one full adder per bit, and more power. A bit serial ALU, on the other hand, works on 1 bit per clock cycle, using the same hardware, repeatedly for each bit, much like a single worker scrolling through the digits one by one. The advantage is a tiny area and low power, but the latency grows linearly with word length n cycles for n-bit numbers. Timing implications. Parallel critical path is the longest combinational delay, often a carry chain. Clock period may need to be long enough for the carry to ripple through all bits. Serial, each cycle has a short combinational path, typically an exclusive, and so the clock can be fast, but overall operation time n times clock period. For a 32-bit word, a parallel adder might need a 5 nanoseconds clock, while a serial adder could run at 1 nanoseconds clock, but would take 32 nanoseconds to finish the addition. Ripple carry adder RCA. An RCA connects n single-bit full adders in a chain. Each full adder produces a sum bit S and a carry out C out from inputs A, B, and carry in C I. The carry out of bit I becomes the carry in of bit I plus 1. The delay grows linearly. If one full adder has a delay of TFA, total delay approximately n times TFA. Numerical example. Add 8-bit numbers 0B001101001 53 and 0B0101110 94. 001101001 plus 0101110. Separator line. 10010011147. The carries ripple from LSB to MSB, taking about 8 times TFA. Carry lookahead adder CLA. CLA speeds up addition by generating carries in parallel. For each bit we compute. Generate GI equals a I.BI. Carry will be produced regardless of CI. Propagate PI equals AI XOR BI. Carry will propagate if CI equals 1. The carry for bit I plus 1 is CI plus 1 equals GI plus PI.CI. Using these equations, we can compute groups of carries with a small logical depth. Log base 2 of n. For a 4-bit block, the carry out can be expressed as C4 equals G3 plus P3.G2 plus P3.P2.G1 plus P3.P2.P1.C0. Numerical example, same numbers as above. Compute G and P for each bit, LSB first. Bit colon 0 1 2 3 4 5 6 7. A colon 1 0 1 0 1 1 0 0. B colon 0 1 1 1 1 0 1 0. G I colon 0 0 1 0 1 0 0 0. P I colon 1 1 0 1 0 1 1 0. Assuming C0 equals 0, the CLA quickly produces all carries, and the final sum bits are SI equals Pi XOR CI. The total delay is roughly the delay of a few ND or OR gates, independent of N, giving a much faster addition for wide words. And a 2-input AND gate gives a .B in a 4-bit ALU. We place 4 AND gates in parallel, one for each bit. Or similar using a 2-input OR gate. XOR for subtraction or parity can be made with 2 ANDs, 2 ORs, and an inverter, or directly with a 2-input XOR gate. Not a single inverter per bit. Shift operations move bits left or right. A logical left shift by one position can be realized with a 4-to-4 barrel shifter. Each output line selects either the same input line, no shift, or the input line from one position lower. This selection is performed by a set of 2-to-1 multiplexers controlled by the shift amount bits. For a variable shift amount, we cascade stages. Shift by 1, shift by 2, shift by 4, and so on, controlled by the corresponding bits of the shift count, the classic shifter barrel design. Multiplexer-based ALU function selection. A 4-bit ALU often uses a 4-to-1 multiplexer for each bit to choose among 4 possible operations, for example, AND, OR, ADD, XOR. The opcode bits serve as select lines for all multiplexers simultaneously, ensuring the same operation is applied to every bit. Encoder, when we need to produce condition flags, for example, 0 flag, an 8-input priority encoder can examine all sum bits and set Z equal to 1 only if every sum bit is 0. This is a compact way to generate status signals from the parallel result. The ALU does not decide on its own which operation to perform - the opcode decoder does. The processor '(S) instruction register holds the binary opcode, e.g. 4-bit code. The decoder translates each pattern into a set of control lines : a LU select (1:0) selects the function 0 0 equals AND, 0 1 equals OR, 1 0 equals ADD, 1 1 equals XOR, etc. Carry in - set to 1 for subtraction 2's complement or to propagate a previous carry. Shift control - tells the shifter how many positions and direction. Flag enable - enables writing of 0, carry, negative flags. A simple truth table for a 3-bit opcode might look like : 0 0 0, a LU select 0 0, carry in 0, shift control 0 0, flag enable 1 and 0 0 1, a LU select 0 1, carry in 0, shift control 0 0, flag enable 1 OR. 0 1 0, a LU select 1 0, carry in 0, shift control 0 0, flag enable 1 ADD. 0 1 1, a LU select 1 0, carry in 1, shift control 0 0, flag enable 1 sub add with C in 1. 1 0 0, a LU select 1 1, carry in 0, shift control 0 0, flag enable 1 XOR. 1 0 1, a LU select don't care, carry in 0, shift control 0 1, flag enable 0, shift left 1. 1 1 0, a LU select don't care, carry in 0, shift control 1 0, flag enable 0, shift right 1. 1 1 1, a LU select don't care, carry in 0, shift control 0 0, flag enable 0, pass through. The ALU control unit receives these signals and activates the appropriate gates or MUs inside the ALU. In micro-coded CPUs, a small ROM maps the opcode to micro-operations. In RISC designs, the mapping is hardwired for speed. When designers compare different ALU implementations, they look at 4 main metrics. Propagation delay, T sub PD, dash the time from a change on the inputs to a stable change on the outputs. For a ripple carry adder, T sub PD is approximately equal to N times T sub FA, while a CLA may have T sub PD approximately equal to log base 2 N times T gate. Critical path dash the longest combinational path that determines the minimum clock period. In a parallel ALU, the critical path often runs through the carry chain. In a serial ALU, it is the path through the shift register plus a small combinational block. Power consumption dash dynamic power is approximately equal to alpha times C times V squared times F, where alpha is activity factor, C is load capacitance, V is supply voltage, and F is clock frequency. Parallel ALUs have many gates toggling each cycle, so they consume more power than serial ones, which toggle only a few gates per cycle. Area silicon real estate dash measured in square micrometers or equivalent gate count. A 32-bit parallel adder needs 32 full adders, approximately 32 times open parenthesis 2 exclusive or plus 2 and plus 1 or close parenthesis, while a serial adder needs just one full adder plus a shift register, saving hundreds of gates. Designers trade these. High-performance CPUs accept larger area and power for low delay. Low-power embedded devices favor small area and serial structures even if they run slower. Q1. Design a 4-bit ALU that supports a ND, OR, add, and exclusive OR. Draw 4 1-bit slices. Each slice contains 2 2-input AND gates, 2 2-input OR gates, 1 exclusive OR gate, and a 4-to-1 multiplexer whose select lines are a LU cell 10. Use a 4-bit ripple carry adder for the add option. The carry in to the least significant bit is 0, and the carry out of each slice feeds the next. Provide a truth table mapping 2-bit opcode to the multiplexer selection. Q2. Derive the truth table for a 1-bit full adder. The truth table enumerates all 8 combinations of A, B, and C in, and shows the corresponding sum and C out values. Q3. Calculate the worst-case delay of a 4-bit ripple carry adder if a single full adder has a delay of 2 nanoseconds. Total delay equals 4 times 2 nanoseconds, which is 8 nanoseconds. Q4. For the same 4-bit adder, if a carry look-ahead block can generate all carries in 3 nanoseconds, what is the overall delay? Delay is the maximum of 3 nanoseconds for carry generation and 2 nanoseconds for some exclusive, or which is approximately 3 nanoseconds. Q5. Analyze control logic. Given opcode 101 binary for a shift left 2 operation, list the control signals that must be asserted. A LU cell is don't care for shift, denoted as X. Shift control is 10, which means binary 2, indicating shift by 2 positions to the left. Carry in is 0 and flag enable is 0 because no flags are needed for a pure shift. These questions test understanding of data path wiring, Boolean derivations, timing calculations, and the mapping from instruction bits to hardware control signals.